Well, hello everyone. Welcome to the talk of building scalable and anti-fragile microservices. It is so couple of words which were there in your agenda are been removed, like Google PubSub and all, because it is a more general talk. Slowly we evolved. We were working at that point of time on Google PubSub, but surely, but with time we evolved. So basically, there are a couple of more generalized technologies which we are going to talk about. So I'm Swapnil Dubey. I have my very good friend Sunil Manikani, and this is our profile. So we basically work at Scalable, and I'm working as a data engineer. Sunil is a data scientist. He holds his primary responsibilities are like visualization, communication, storytelling, predictive modeling. So almost all the things which we just saw in the last session, and the technology stack we are using here are Keras, TensorFlow. We are using a lot of Python and all. For me, it's more of my roles and responsibilities are ingesting real-time data, doing some aggregation, constructing numpys for the data scientists to consume, and finally storing the data into data stores. So these are kind of our jobs which are like in the Venn diagram, they are completely different. But there are a couple of responsibilities which we share, and the very first one is actually about infrastructure for running of your data science jobs, especially when we talk about big data. Right, so those days are gone when you have couple of MBs of file, and we are processing and we are running our models on top of it. Just to give you a number, we have a data set where we are using actually we are sampling it out, and we are using just 3% of it, and still it is taking approximately 12 hours using Keras and TensorFlow on a bare metal machine, right? So one machine with couple of GPUs, so it is taking that kind of a time. And it is just 3% of data. Actually, when we will go in front of the customer, we will train the model for the rest of the 97% as well, right? So for us, it is very important to talk about infrastructure for running of the DS jobs. We are looking into parallelizing our data, right? So our model are going to run in basically data parallelism while running the models, as well as we are looking into model parallelism as well. So we have our models that should also run in distributed way, couple of components here, couple of components there, and so on. So the agenda for the talk will be, we are going to describe a problem statement, what exactly we were facing. We will talk about the possible solutions which are being used across industries, which are pretty straightforward and simple ones. A lot of YouTube videos are available on top of it. We are going to present our solution. Then we will talk about benefits of our solution, what exactly were few benefits which we got from them. We'll talk about few building blocks for our demo, which is the third part. We'll have a 5-10 minutes demo of just to convince you guys that yeah, it is the technology to look for. And for that, we have to build few blocks, and we'll talk that into part 2. So this is our problem statement. Schlumberger is a historical company, more than 100 years old. We have a lot of patent data sets. We have private data, public data. There are different ways to read it. Historically, our teams had developed code for reading the data into C++. They had used C as well. And right now, like what development we are doing, we are writing it in Python. We are using Java for it. For doing parallelism, right? So there is a concept MPI, message passing interface. So we are using MPI specifically for parallelizing our R jobs. R is nothing but a statistical language which we use, and it is primarily a serial language. I mean, everything runs serially, but we had made constructs which can basically parallelize that. So one piece of R is going to execute on one of the machines, and the other piece is going to run on the other machine. Our jobs have different scalability and resource requirements. So there is absolutely no point if our job can run on one core on, let's say, 5 GB of RAM, right? If we allocate, let's say, 3 cores to it, it is a waste of resources, and it might seem very simple, couple of dollars per day, but in the long run, when you have the models deployed in production, it is actually going to affect the cost thing. So we wanted to have, let's say, if the model requires just 1 core, we require just 1 core of that machine. So we need to have that thing in place. The other thing which we wanted to have is that, as I told, that we have a history, and we use a lot of technologies, a lot of languages, a lot of ways to process. The other thing which we are facing right now is, though after moving to cloud platforms, we don't want to, like we are right now using Google Cloud Platform for our development, and the demo which we are going to show is also on Google Cloud Platform, but we don't want to bind ourselves to Google Cloud Platform. So it should not be a case that our code and everything, our pipeline cannot work on Amazon, AWS, or for that matter Azure, right? So we wanted to have that kind of freedom, and that is the reason why platform cloud infrastructure specific components, we cannot use them, right? For example, we cannot use AWS Lambda, because the moment we are going to go out of AWS Lambda, it is not going to be supported, right? For that matter, the same thing is with Google App Engine, right? So Google App Engine just supports Go, Python, Java, and one more, I think. So it is a strict condition that we need to write the code in these languages and somehow do some dirty things and try to execute a C++ code from Java and whatnot, right? So we don't wanted to have that. We wanted to have a very clear and clean way to implement everything. Our jobs involve multiple steps as well, right? So it can be a case that one script ran, one Python code, a piece of code executed, it produced some output. We wanted to have that as input to the other Python script, right? Pretty straightforward. I mean, everybody does that, but we wanted to have that in the generic infrastructure what we are providing. In addition to that, we have distributed teams. So we have teams sitting in US, and they work at night, we work in the morning. Our models can run for 12 hours, right? So the thing is that we just cannot guess the amount of infrastructure which is required at any point of time, right? I can have, let's say, 100 nodes of 4 vCPUs running, but it can be a case that suddenly the data science people come up and they try to just spawn everything, and that spawning, maybe they are using any of the distributed concepts which I just talked about, the model and the data. It spawned, it required another 50 machines, right? So we cannot simply judge at any particular point of time that how many machines are required. And those who have experience in working data science team, data science people simply don't love to spawn and do all those infrastructure related. They wanted to be into maths and and the SVMs and those kind of stuff, neural networks. So we didn't want to put that kind of a burden to them. So our infrastructure should scale up automatically, right? So it can be a case that at night it was 200 nodes required and 200 nodes were spawned. The other thing which is important is, once the task finishes, it should downscale itself, right? Otherwise, in the morning, it is going to be another dirty job, maybe for a data engineer to select them or for an infrastructure guy, right? So auto scaling and downscaling auto upscaling and downscaling should be there, provided in the infrastructure. Next, we have a shared nothing architecture, pretty straightforward. Our jobs should not, I mean, if you have a Python job running, it should not have any kind of effect on any other jobs which are there. So basically it should have its completely separate VMs, it should not share anything. But there is a requirement of sharing the data, right? So one of the scripts produce something, where will it keep the data, and the other script will be going to use it. So if you look into various high performance computing papers which were published, they talked about network area storage, and when you look into any of the documentation what Amazon or for that matter Google provides, they talk about creating the VMs in the same zone and putting the data into S3 or for that matter Google Cloud Storage. So it starts appearing as a local data for you. And the very important thing is we basically wanted to have a job execution kind of a framework. You submit a job to the cluster and just forget, you will get a mail once it finishes off, right? So these are the possible solutions which anybody can think of. I mean, it would have come in to a lot of people. We can have dedicated VMs, right? We just use a bare metal machine which has been provided either by Amazon EC2 nodes or for that matter VMs which we have in Google Cloud Storage. But the problem is the infrastructure impedance mismatch, right? We require 5. The moment we require 10, there is some kind of an infra task associated with it. We don't want to have that. It requires physical spawning and stopping of the VMs, as I told. Second can be deploying everything as managed microservice on Google App Engine and AWS Lambda for that say. The thing is that, of course, auto scaling and downscaling can be achieved out of it. How they do it, that is their headache, but yeah. it is not like it is not cross cloud provider kind of thing. So we got away. I mean, we don't wanted to use that as well. So this is something what we provided. Of course, this is not the complete complete architectural diagram, but frankly speaking, before thinking in this direction, we did some. This was one of the initial diagrams which we created, and what all spikes we did just to be sure that yes, this is going to work. We are going to demo that actually. It is not going to be the complete thing. So what we do is we have an admin module. This is running as one of the virtual machines because it has to be up and running every time. And frankly, it is not going to be, it is not going to have a load of like 100 requests per second or 200 requests per second, right? It is a very simple one. So we have a couple of cores associated to it, and it is a bare metal machine where we had our admin module. This admin module gives a job submission UI where you can submit a job, right? You can upload a file from the button and it will execute. What is happening behind the scenes, on which machine it is executing, that is altogether a different thing. They don't have to see that. All that is data scientists know is once you run everything in a local, and if it works on a small data and you want to check everything on the complete data, you have to log into the admin module, upload a file, run the job, and once you get the mail, you can go ahead and look into the Google Cloud Storage or S3 buckets and have a look of the results. So we have various kind of jobs. We have submit Python job. We have our jobs which we are submitting. We are using MPI jobs as well. Basically, MPI jobs not that famous right now after these distributed computing frameworks like Hadoop and all. But yeah, we are using it at some level because R is not being provided. We don't want to use Spark R and all. Our scripts are pretty simple, so we simply parallelized it using MPI. We are submitting Java jobs, and this again is running on virtual machines. We don't want. Why we are using virtual machines is because, again, we don't want to stick to Google Cloud. So we have that on a single Ubuntu 17.0 something running. What it does is, this is my PubSub layer, and in the agenda it is written Google PubSub, but we have generalized it. So we don't want to stick to Google PubSub. It is more of Kafka and all are available. So they act as producers. So whatever request you are submitting, it is a JSON is created and it has been submitted to a Java job topic, right? So we have topics for all the frameworks what we are having. Once a data is successfully placed within the callback feature of the producer, we are putting a data into our admin module into the DB that this has been submitted, and and why we are updating every time, because we wanted, the moment we go into that admin module, we want to have a look of what all is happening right now on my cluster. What happens is we have a consumer, it basically takes the data and submits it. It creates a YAML file, to be frank, right now. It creates a YAML file and submits it to a GKE cluster. We are right now looking into COPS as well. I mean, GKE is for maintaining Kubernetes cluster on Google Cloud, and we have COPS for managing that Kubernetes cluster on AWS. So we are looking into it. We have our Docker images. So on this Kubernetes cluster, we spawn a pod. We run that job, maybe a Spark job or an R job. Spark is still in progress, kind of. It is not confirmed, but yeah, we are looking into it because people had started talking about putting Spark on Kubernetes. So a point where you guys would love to read what exactly is happening. But yeah, we are doing that for Java, Python, and R successfully. And whatever custom images we are creating, we are putting that into a container registry. For EC2, we have an option of EC2 container registry, and for Google, we have a Google container registry, right? So apart from having all the must-haves which we had in the very first slide, we have these four to be precise, four benefits, additional benefits. Like I said, we need to have the horizontal scaling. So if I'm running 2 jobs today, it should have 4 nodes. If I'm running 100 jobs, it should have multiplied by 100. So your infrastructure should scale up. We need to have rolling updates. So there are, as I said, we have historical use cases and historical products running, and they have very specific requirements. For example, they are working on Python, historical Python version, and it is running pretty fine. We don't want to disturb that, right? Since it is running and it is adding value I mean, it is basically generating revenue. We don't want to disturb that. We just want to use the same environment and deploy it. So rolling updates is available. If you want to have a new service on a new Python, it is available. If you want to have an old Python version running something, it is available. The only difference is the creation of the container, right, or the environment. It is a cloud native job-like infrastructure, right? So cloud native in the sense, it is we are right now targeting 2. But of course, at some point of time, we'll talk about Azure as well if required. We have few people who are using Azure as well. And it supports both. It's not the case that the container can just, container launches, it runs and it goes away. You can actually deploy your web service, your actual web modules on top of it, right? And you can have that tolerance which is provided in Kubernetes out of the box, where if any of your services goes down, it again puts it up, right? So we have both persistent, maybe a web module, like in our case, it is an admin module. Though we are not hosting it on Google container engine, but yeah. And we can have non-persistent applications. Maybe a TensorFlow with Keras code which you want to execute. It takes machines. It launches container. Maybe your container requires more addition of resources during the runtime, and finally it goes away, right? So we will look into this, how we are doing it, how we are actually looking at the Google container thing. But for that, that demo to be meaningful, we have some building blocks for you. So I will invite Sunil for taking us forward.
Okay, so thanks, Swapnil. This is the part 2 of the presentation, and thank you for talking good things about data scientists. Nice to hear from the data engineering team. Right, okay, we come to expert talks, and I have a box and 3 boxes. Okay, right, so I mean, what Swapnil is talking to, I want to lead you to what microservices are, right? So it's very essential to come out of the monolithic world and talk about microservices. Right, so you can see those rectangular boxes over here and 3 separate boxes. Right, we want to encourage the microservices way of thinking. Right, so now consider all these geometric shapes as your services, right? So initially what you should do is keep everything tight in one box, right? And you need to get out of that mindset, right? Because what happens is, say for example, to do data parallelization, maybe Spark is better, data flow is better, and need to go to Java. But when it comes to writing data science codes, right, it is more important that you focus on R and Python like scripting languages. Right? So you need to come out of one stack solution and think of, you know, independent boxes, right? So once you do that, right, what are some of your advantages? Right, you have a faster startup time for each of these individual boxes, right? And they can scale up independently, right? So the whole topic is about building scalable and anti-fragile technology. So, I mean, the building block of this is microservices, right? Because each of this service can be kept independent of each other. And once you've kept it independent of each other, you can scale it. Right, and one thing which I want to tell you is that now each of this service runs inside its own lightweight app server engine. Right, now I need a technology, I need something which can help me achieve that. Right, so in comes Docker. So in 2012, 2013, this technology started and it took a big boom. Right, so again, let me repeat the problem. Right, the problem is keeping all your lightweight stuff, making it as a microservice, keeping all your blocks independent of each other so that you can scale them, right? So you basically talk of containers now. You put them in actual containers which allow you to develop and package your application and all its libraries all together, right? And Docker is just a tool which will help you basically create, deploy, and run applications by using this container mentality or container philosophy, right? So now what happens? Right, you've developed your containers, but then suddenly there's a boom, right? There are a lot of containers. So in comes, to rescue, in comes Kubernetes, right? So on the left-hand side, you can see, right? So now you have ocean of containers, but now you need to manage all of it, and there comes the Kubernetes master, right? So what the problem is really is that you want to roll out your new features seamlessly, you want to scale your applications on the fly, you want to limit your hardware usage to, you know, so that your resources are equally occupied, right? So how do you schedule and package these containers onto these nodes, right? So in comes Kubernetes to save our life. Thankfully, we have the Kubernetes technology which is able to manage all of this for us. Right, so let me do a little bit of analogy of what Docker and Kubernetes would look like. Right, so the Kubernetes is that ship, the K8s, right? It's also famously known as the cloud operating system. Right, and your Dockers actually are fitting on top of it. One thing which you want to note is that I'm showing you a ship right now, but you could imagine a rail carrying all these containers or a truck carrying all these containers. Right, so all these technologies are kind of independent of each other as well. right? And to focus on the anti-fragile part, right, we have something at Google which is Google PubSub, which we heavily use. So in the demo, wherever you'll see a publisher and subscriber, I just want you to imagine the underlying technology. It's actually Google PubSub in our case, in the demo which we're showing you. It's a fully managed real-time messaging service. Think of it as big brother to ActiveMQ or some of the message passing technologies like Kafka. Yeah, so Google PubSub is responsible for passing messages independently between applications, right? And what we did is we kind of collated everything, and we have a demo for you, right? I think this Swapnil is going to show the demo, and then we'll take up questions.
Yep. Basically, when we started with this, when we started to create this infrastructure, we were pretty sure about how this will work, right? Mechanisms available in the market, maybe Flume or Kafka or combined Flume and Kafka, which is Google PubSub, which has both pull and push technology features available, right? So we were pretty okay with all these things. What we want to show you is the things that whether it is actually scaling up properly or not. I mean, it should not be a case that it is failing, right? What all are the pain points for us to actually deploy something on Kubernetes? How to create those Docker files? Normally, when we talk about Docker, we have a file, right, where you specify that install this, install second component, third component, and finally you basically start that container, right? And ideally speaking, in the market it is said that you should not, your Docker container should be a static one. It should not, at the runtime, it should not happen that maybe your code versions are changing or you are pulling something out of it, within the container, right? But our case is pretty different. Our case is kind of use it and throw kind of a thing. So we actually got away with that, and we have within a Docker file we are actually pulling the new code and running it. So if I'm a data scientist and if I want to execute anything, what I can do is either I can upload from the UI, right? So it will be available in an area within GCS. From there we are going to pick it up. Or what we can do is once you are okay with the results and everything, we will schedule it, right? So in that case, we will create a job description file, right? Something which was created initially by the UI. We'll have that job description. We'll put that into maybe scripting shell file, and it will keep on executing. So let's see how this happens. To be frank, these are few of the features which I wanted to highlight, and these are actually the questions which we started up with. I mean, if we have an answer for all of them, we are pretty good. I mean, for us, everything was student, so we just wanted to have answers for this. Right. So, just a question. How many of you have actually installed Kubernetes infrastructure, maybe on wheels? So how easy it is? I mean, I'm talking about the general VMs, right? It should not be any of the supported way to do it, right? So it has multiple steps. I mean, it is of course doable. It is possible, and it is pretty simple, but you have to follow a lot of steps. And these Google Cloud Platform, whether you talk about Google Cloud Platform or whether you talk about AWS, they are giving you this opportunity to actually manage your. They basically spin up your Kubernetes cluster from the UI only. So it is pretty less. The amount of steps needs to be taken is pretty less, to be frank, in comparison to if you're going to do that on one of the VM. Right. So this is in Google. It is so that's container engine basically, and I have one container engine which is running, or for that matter, a Kubernetes cluster is running, which has just one cluster size. So since we don't have any jobs running, so it is just one node which is there. So of course, even if your infrastructure is not being used, you are actually paying for one of the VMs, right? Ultimately, it is a VM. What happens is for zone, when we select a zone, basically, right? For example, right now it is US Central 1A. Why we choose for a particular zone is because our data which we are processing is actually present in a Google storage, which is there in that same zone, right? And Google actually says that it is nothing but a network area storage for you. So the reading and the writing and the amount of money involved to transfer via network, that is pretty less, right? We are using a particular Kubernetes version, and just to state one more fact that let's say there is a release of Kubernetes, you can actually auto upgrade, you can have those alpha features as well, right? There are few alpha features right now. Alpha features are those where basically those are still not production ready, but yeah, you can use it for your experiments. Those are available out of the box. You can just have a click and you can do it. Apart from that, if anything comes into my mind, I will get back to this. So let's move. Now I will like to show a simple VM instance. So this is a VM. This is nothing but ExpertTalks. If you see the very first one, so this ExpertTalks is the VM which is actually the VM where we will do an SSH and we will start running. From there, it is a jump host. Basically, from there we will execute everything. And the second VM is that one VM which your Google Container Engine is using, right? So it has just one. So let's do it. So this is pretty simple code snippets. I have our jobs to show you the auto scaling features and all, but those are nothing but just printing of the statements. We are just printing it out. The main focus is on how our containers are being spawned of different types of 2 core, 5 core, 10 core, right? And how well it scales up, and where exactly is the restriction, right? So with everything positive and high, there is a restriction as well. We'll talk about it. This code is hosted as well, so if anybody wants to go ahead and look into it, they can go ahead and look into it. Google, for your information, Google gives a $300 kind of account to you where you can go ahead and practice all these things. So maybe a nice starting point. No idea about AWS, to be frank, because we had not used it for quite some time. We had started using it and actually deploying few of the things, but no production. No personal usage. We had not used our personal accounts for AWS. Right. So let's start. If we go into ExpertTalks, so we have a folder which is R. If you see, there are few files here. So there is one Docker file. As I said, Docker file is nothing but it just install this, install third component, fourth component, and you write few of your things. For example, if your application is hitting a MySQL database, you can actually put your user ID and passwords. Of course, you have to keep them secure. Those things apply, but we can put everything here. So if you see, I'm using this where I'm installing everything. So if you see, our people actually use quite a lot of things. Like, for example, I installed a version of R someday, and then they came up with installing Microsoft R Open version. Then they come up with something other. They started using Stan, and these are few of the libraries what we had. So we have Excel Connect and all. So you can package everything, all of these things together, right? So the thing is that once a data scientist comes and he tries to execute something, and if everything starts installing at that point of time, or even for that matter, if you are actually creating your Docker images, it will take a lot of time, to be frank. So we need to have everything, all these settings, right? For example, I'm creating a directory. I'm pulling the code from this. So this is github.com. Swapnil, say hi to Swapnil. ExpertTalks. So whatever code I'm using, it is there. I'm pulling all the codes, and finally I'm trying to run something, right? So it is setting up of my environment. Similarly, we have Docker files for running TensorFlow Keras, right? Similarly, we have for Python, Java, and everything, right? Pretty straightforward. It is available in Docker Hub as well, but yeah, it is public, so depends up to what level you want to use it, right? Now with this, we basically do a build kind of a thing. So if you see this, so what it does is it basically creates a build. It will use this Docker file and it will build an image for us, which is going to be there on my local machine. And from this local machine, I have to push this image to my Google Cloud platform so that it can be used from there, right? So we can build it like this, right? And we can push it like this, right? So these are very specific things. So this is actually actually the way we push the things. So for example, GCP experiments, a number what you're seeing here is actually my project ID. So whatever project ID I'm using, it is the same thing. Bookshelf at the last is something what we created. So whatever Docker image we created, it has the name bookshelf, and I want to push that into my container registry. Right? We can have a look as well. What all is there in this? So you can see there is an R image available, which ultimately is saved on your Google Cloud storage. So the thing why I'm telling this is the migration will be pretty simple, right? Whatever images are being created, it is more of a migration from one storage to the other. Of course, there are few hiccups, but yes, it should ideally be smoothless. It should ideally be smooth, sorry. Right. So with this, we'll get to a simple pod definition. It is very simple one, where we are actually doing it. So if you see, it has a name. So this pod is nothing but a job definition. So whatever jobs we are submitting, whatever parameters we are asking from the data scientist, from the UI, are actually being converted into a YAML file, and this YAML file is the one which is actually getting executed on the cluster. So if you see the container definition there, right, fourth line from the top, that container definition is actually the definition which is of prime importance to us, because that is a place where I'm saying that. So basically, we pulled the code, right? We pulled the code in the Docker image only. The moment we created the Docker image, the moment we start the container, the Docker image, while it is coming up, while the container is coming up, it will pull the code from the GitHub, and finally it will actually point to the master, right? So we have the master branch being informed here, as well as the SHA code. So let's say if you have a code which was running fine, and if somebody goes there and just modifies that, you can actually run that code again, right? Because we are linking that to a SHA code, and it is pointing to that specific commit. Then we have something known as r-r script.r, which we are going to execute, and we have the input and the output. So the thing which you want to tell is that we are populating all the parameters which were there which were inserted by a data scientist. We are putting all that parameter as an argument. So you can, once your container is up and running, you can actually push a lot of arguments as well. For running this container, if you see, I'm using this image, right? So it is that same image, kind of image which was there in your container registry. It is using the same image, and this is the resources. So if you see, this is the limits what we are putting to. So your container is not going to swell after one vCPU, right? So it is not going to be more than one CPU if required. It should have this much amount of memory, and this is a request. So let's say if the container starts with something in some initial size, it can actually request for more resources in a discrete step, which is going to be of these values. So it is going to ask for one CPU and this much amount of memory to execute again. So each of the job submission, whatever job we are submitting, let's say if it requires 4 Python files to be executed serially, right, one on the input to the output, there is an infrastructure, there is a script which actually accepts all of this and actually fires this command, to be frank. If you see, it is rsample1 created, and there is a UI as well with Kubernetes, where you can go ahead and look. So with the name of rsample1, there will be a job here, right? So it should come up. So actually, my VM was not pointing to the right container engine cluster, and we actually connected it through the VM. And finally, we have this R jobs being executed. If you see, this is a job and there is a pod. So Kubernetes has their own philosophy and thinking that your job will not be terminated. So even if your job finishes completely, it is not going to be terminated, right? So the disadvantage, the theory which they tell us is that the person who has fired a job on Kubernetes should actually have the capability of looking into the logs and all. But frankly speaking, if we have that kind of a situation where the jobs are not terminating, in that case, my cluster will not come down, to be frank, right? Resources are still being used and the job is still there. So for that, we have another, if you see, we have a completed job for deletion. And this completed job for deletion does nothing. It simply runs a script, and it basically runs a code, a piece of code, which is running in an infinite loop. So it is never going to terminate. But the thing is that whenever it runs, within each execution, at let's say after a couple of seconds, it checks for all the jobs with what had finished, right? So whatever jobs had finished, maybe after a duration, within a duration of 5 seconds, it will simply terminate everything explicitly. So ultimately, what you will see is that after 5 seconds, what all job has finished, that will be completely removed, right? The only thing which I want to show is, let's just fire a lot of them, right? So I have different pods and all running. We should ultimately see our cluster going up, right? Our node should go up, right? So it is right now my sample 3 job pod basically. I mean, this pod is actually a part of my job 3. Is actually facing the issue of insufficient CPU, but it is not going to be a case that it fails. It will automatically spawn 1. So within that UI, you will see that there are now 2 nodes, and ultimately it will succeed. So it can take a bit of time, but yeah, it will run. So if you see, we have we looked into simple Kubernetes creation, cluster creation. We have the auto scalability. Of course, that will take a couple of minutes. So we'll get back to this. I will show the results that it is 2 now. We have the concept of preemptible VMs in Google Cloud basically. So that is something which we are using heavily. And by preemptible VMs, it is nothing but you just select one of the checkboxes. It becomes preemptible. It becomes preemptible, and it says that it is going to be. It takes. So let's say a normal VM takes $10. It is going to take 1/3 of 10, right? So it is very less. I mean, in terms of cost, it is pretty effective. And plus, it is almost 100% sure that your whatever preemptible VM you have, it is going to terminate in 24 hours, right? So we can use this preemptible VMs in our case, because if you see, we have a use case where suddenly we require maybe 100 nodes, and at the next time we ourselves are going to kill it. But if in case anything happens, let the Kubernetes do the fault tolerance for you. And if it is missed by Kubernetes, what we do is, if you go here, if everything fails, still we put an entry, we hit a REST call which updates our DB with a failed status, and this whatever jobs we have at the failed status, it is again going to be submitted to our topics. So because of the infrastructure issue, it is not going to fail. Any of your jobs is not going to fail. It can be a case that it takes time. For once in a while, it can take a lot of time, but yeah, ultimately it will run. Now, only point which, sorry. So we looked into creating, building, and pushing images to the container registry. Job definition, auto scaling feature. I will just show the result. Increasing the resource allocation for the pod. So whatever request parameter we saw in the container definition, that was asking for resources. And the last point is, what if we asked container resources greater than their actual VM size? So here we had a VM of 4 vCPUs. Let's say in the container we go and describe that my cluster should have my container should have 10 vCPUs, right? So there we have something known as a concept of pools, right? So we have node pools. We have different kind of definitions. So we can have a node pool definition. Node pool is nothing but a specification which will spawn VMs at the runtime with whatever nodes you configure for. So like here we have a default node pool with a size of 4 vCPUs. We can define our node pool with a size of maybe 10, 15, 20, whatever you want for. So that's pretty much it. If required, you can get in touch. If anything, if this excites as an infrastructure, you can get in touch. We'll be more than happy to help you. The GitHub link is below. So for the initial practice, you can do that. We are open for questions now. Thank you.
Hey Swapnil, thanks for the talk. I have one question. Like, How did you arrive that? How did you arrive that for this much input, you will require that these resources? Is it a hit and trial, or after certain experimentation that okay, for if this is my input size?
It is an experimentation.
That's it.
It is an experimentation. So the thing is that let's say I have a script, okay, which takes maybe a couple of GBs, which is taking as input couple of GB of data, right? We run it with the base, right, with the 4 default node. It should ideally run. If it does not run, we increase the size to the next pool. That's pretty much it. But the thing is that we have the class of scripts, right? Even if you're using, let's say, 2 GB of data as input, we can have different scripts which can take 4 CPUs or we can take 10 CPUs as well. So we need to have some kind of knowledge beforehand that what should be the ideal container size for it, and we should put that using that same node pool.
So this logic is automated, or this is something that is, a human has to sit in front of the computer?
So right now, we would love to have that automated, but frankly speaking, right now we have that manual intervention there.
All right, thanks.
Yeah.
Hello. Okay. So 2 questions. Okay. First one is in your benefit solution slide, you mentioned rolling update feature.
Yeah.
So rolling update is kind of thing already supported by Kubernetes by default. Okay. So are you using Kubernetes feature, or what you have done extra for your primitive VM?
So frankly speaking, with rolling updates, I just wanted to tell the point that we can have same script, so let's say I have a script which was running on, let's say, Python 2.7, which is actually right now supported by Google Cloud Platform, okay, and we wanted to have an experiment like which moves to 3 point something, so we can do that kind of an experiment. So it is not going to affect the previous one. So we are updating the technology stack for the scripts.
Okay, one more question.
Yeah.
So what happens in the case of job fails? Like, can you run those events again and replay your jobs?
Yeah, it will be automatically updated. If you see, the moment if my job fails, I have a script, I just talked about that infinite loop, right? It checks periodically that what all jobs had failed, and it updates that same thing into my architecture, if you see.
So my question on what happens, what are you storing in your database? Can you replay those events again?
Yes.
To rerun
Yes.
your jobs?
So what happens is that same thing with the failed status. I don't know whether you can see this. It is pretty blurred, but we have that same job which has been inserted with a failed tag, and that failed jobs, a periodic thread runs, and it again puts that into the topic. So it can be a case that some issue happened, right? Due to VMs, maybe due to your preemptible VMs going down, your job failed, right? But that job is actually a contender of finishing itself successfully, right? So it will eventually succeed in couple of runs. Yeah.
Thanks.
Thank you.
Hi Swapnil, this is Tripathi from Taviska Solution.
Yeah.
I just have one question, that apart from being the cloud agnostic approach, is there any particular reason that you have used Kubernetes?
So I think cloud agnostic in itself is pretty important for us.
You're not sticking to a particular cloud vendor, that you want your solution to be cloud agnostic.
So let's say you have a Spark cluster running. Okay, people talk about big data. Everybody is using Spark right now. It is a general knowledge kind of a thing now. So you have a Spark cluster running. Okay, so what you do is you have 10 nodes where your Spark is running. Even if you run a job or you don't run a job, those 10 clusters are going to be there, right? You are actually paying for it. But if you use this, if you have a Spark job, it will use a Docker image. However, this is still in beta phase. It is experimental. You can read a lot about them, but as an example, I was reading it, so I'm telling you. So when your Spark job comes, it will spawn a node. It will spawn the VMs. It will increase the number of VMs. It will run the job and finally go away, right? So here it can wherever you have a condition where you have we need to be double sure. Where you actually put a fixed condition on your infrastructure and then you wait for periodic jobs to come, and then it will be utilized. I think you can just get away with all that. And frankly speaking, it is really cost effective when you talk about the preemptible concept which I just talked about. So that the cost effectively comes out to be 1/3. You can go ahead and look into the documentation. So if it requires $12 per day, it will require just $4 per day. So that again makes it very effective.
Is the cost the reason that you have used Kubernetes?
Cost is in itself a big reason. So cost is a reason, cloud agnostic is a reason. The type of jobs, if you see, if you talk about using Google App Engine, for example, or any of the Google technology, you are bound to use Python 2.7. I want to run, I have my latest Keras, which is maybe releasing, I think today, 11th November. It can be on Python 3 dot something, right? And I want to run that experiment. How will you do that?
Sorry folks, we're going to stop the Q&A session now.
Yep.
If you have any questions for Swapnil or Sunil, please
Yeah.
do reach out to them offline. Yep.
Sure. Thank you.
Thank you, Swapnil. Thank you, Sunil.